Every turn-by-turn navigation system, every game that finds a cheap path across a map, and countless network protocols are solving the same abstract problem. They need the shortest route from a starting point through a web of connections where each link has a cost. That cost might be minutes, miles, milliseconds, or money. The algorithm that powers most of these systems when weights are non-negative is Dijkstra's algorithm. In this video, we will build intuition, walk through a full example, and see how to implement it with a priority queue. We model the world as a weighted graph. Vertices are places or states. Edges are allowed moves, each with a weight that must add up along a path. The single source shortest paths problem asks, from one start vertex, what is the minimum total weight to reach every other vertex? Unlike unweighted breadth-first search, we cannot just count hops. A path with fewer edges might be more expensive if those edges are heavy. Dijkstra's method is designed exactly for this weighted setting, as long as every weight is 0 or positive. Here is the one rule you cannot break for classic Dijkstra. Edge weights must be non-negative. The algorithm repeatedly locks in the vertex that currently looks closest to the source. That greedy step is only correct if a shorter path cannot appear later through a cheaper negative edge that pulls the total down. If negative weights exist, that assumption collapses. In practice, you either remodel the problem or you switch to Bellman Ford, which allows negative edges and detects negative cycles. For the rest of this video, we stay in the non-negative world where Dijkstra shines. Dijkstra combines two ideas. First, greediness. Always finalize the unsettled vertex with the smallest tentative distance from the source. Because all remaining edge weights are non-negative, no future path can make that vertex cheaper. Second, relaxation. Whenever you settle a vertex U, look at each neighbor V. If going through U improves the best known distance to V, update it. The textbook relaxation rule is, if distance to U plus the edge weight is less than the current best distance to V, replace that best distance. Repeat until every vertex is settled or unreachable. How do we always fetch the smallest tentative distance efficiently? We store pairs of distance and vertex in a min-priority queue, typically a binary heap. Each time we pop the minimum, we settle that vertex if it is not outdated. When relaxation improves a distance, we push the new pair. Duplicate entries for the same vertex are harmless. When a stale larger distance pops first, we skip it. With a binary heap, each push and pop costs logarithmic time in the heap size, which leads to the familiar bound order of the quantity V plus E times log V for sparse graphs. Fibonacci heaps can improve the theoretical bound for dense cases, but binary heaps are what most engineers actually code. Here is a compact Python version using heapq, which is a min-heap. We map each vertex to its best distance, initialize the source to 0, and everything else to infinity. The heap stores pairs of current distance and vertex. When we pop a vertex, we skip if we already processed it, which discards stale heap entries. For each neighbor, we compute the candidate distance through the current vertex. If it improves the record, we update and push. When the heap empties, the distance map holds the shortest path weights from start. To reconstruct actual paths, store a parent pointer whenever you improve a distance. Let us run the numbers on a concrete graph. Vertices S, A, B, C, and T are wired with the weights shown on screen. We start at S with distance 0. Every other vertex begins with unknown infinite distance in theory. In code, we use a very large number. The priority queue initially contains only the pairs 0, S. The algorithm will repeatedly pull the smallest distance, settle that vertex, and relax every edge that leaves it. Watch the next scene as those tentative numbers shrink step by step until we know the cheapest way to T. First, we settle S and relax its outgoing edges. A gets distance 1 because the edge from S costs 1. B gets 4. Next, we settle the smallest unsettled label. Relaxing from A improves B to 3. Because 1 plus 2 beats 4. We also reach C at cost 6. Now, B has the smallest tentative cost, so we settle B. That drops C to 4 and pushes a path to T at 9. Finally, we settle C. The edge to T costs 3, so T drops from 9 to 7. 7 is optimal. The path S to A to B to C to T adds 1, 2, 1, and 3. No cheaper route exists under non-negative weights. During the run, whenever relaxation improves a vertex, remember which predecessor caused the improvement. Chaining those parents backward from the target reconstructs the shortest path. Visually, the edges that actually participated in those improvements form a shortest path tree rooted at the source. On this example, the tree follows S to A to B, B to C, and C to T, with total weight 7. The same algorithm scales to millions of edges as long as your priority queue operations stay fast and weights stay non-negative. It helps to park Dijkstra next to its cousins. Breadth-first search solves unweighted shortest path in linear time in the size of the graph, but it ignores edge costs. Dijkstra generalizes that idea to non-negative weights with a heap. Bellman, 4 allows negative edges and runs in order of V times E, which is slower but sometimes necessary. Johnson's algorithm even combines Bellman, Ford pre-processing with repeated Dijkstra for all pairs shortest paths on sparse graphs. Choosing the right algorithm is mostly about which weight rules your problem allows. You have probably used Dijkstra without knowing the name. Link-state routing protocols, such as OSPF and ISIS, run a variant of shortest path first on a map of routers and link costs. Games path find on navigation meshes with movement costs. Logistics engines minimize time or fuel on road networks modeled as graphs. Social and knowledge graphs sometimes use weighted shortest paths as a building block for ranking or similarity, though production systems add many extra heuristics. The pattern is universal. Model connections, assign costs, run shortest paths. Here is the mental model to take away. Dijkstra assumes non-negative weights, repeatedly locks in the closest unsettled vertex, and relaxes edges to improve neighbors. A min-heap makes each extraction cheap, and skipping stale heap entries keeps the implementation simple. Store parents if you need the path, not only the distance. Complexity is order of V plus E times log V with a binary heap on typical sparse inputs. That combination of clarity and performance is why Dijkstra remains the default single-source shortest path algorithm taught in courses and shipped in real systems. Thanks for watching, and subscribe for more deep dives like this one.